Good evening, Dr. Dolapo.
Welcome, sir.
Yeah.
Yes, sir. I think we can start. Once more, I welcome everybody. Today we look at Factorial ANOVA. And in the last few weeks, we have been talking about ANOVA. We'll be talking about ANOVA. Today we want to quickly look at Factorial ANOVA. Factorial design. We want to quickly look at factorial design. There are some situations when the factor you are looking at is more than one. There are more than one. What we have been looking at in the last few weeks is one factor ANOVA, which is one-way ANOVA. So, for example, the case of libido among three groups, comparing libido among three groups. Group 1, those with placebo that took placebo. Group 2, low dose Viagra. Group 3, high dose Viagra. These are three groups. And it's only one factor. The only factor we studied there is the Viagra, effect of Viagra on libido.
Hello? Hello?
I was muted. I'm not here. Hello? I think everybody can hear me now.
Yeah, yes, the voice has come back.
Yeah. I didn't know
Yes,
that.
I can hear you now.
Okay,
I
when
can hear you now.
I forgot when it went up. Sometimes when it goes up like that, the host will be muted. I didn't notice. I just okay. What I was saying was that whenever you are having two factors, more than one factor involved in ANOVA, it is called factorial design, factorial ANOVA. Mind you, the number of factors is different from the number of group we are comparing. We all know that whenever it is when we are comparing 3 or more groups that we use ANOVA. When we are comparing the means of 3 or more groups, we use ANOVA. So you can have 3 or more groups, 3 group, 4 group, and it's still one factor that is involved. That case is one-way ANOVA. For example, the case of libido and Viagra. We talk about the example of libido and Viagra is one-way ANOVA because it is only that factor, one factor, the Viagra, that define those 3 groups. So one group, no, you give placebo, second group, low dose, third group, high dose. So it's still one factor. Though we have 3 groups, it's still one-way ANOVA. You can even have 5 or 6 or more than 6 groups. It's one-way ANOVA because it's only one factor that is defining. It's just the one factor. It's only that is the one factor that defines them to the more than 2 groups. And I said that if let's say you only have placebo, and one dose, maybe you don't talk about high dose or low dose, one placebo Viagra. You're having 2 groups. You won't talk about ANOVA, you'll be talking about T-test. But because that particular Viagra has defined them into placebo, low dose, high dose, so we are having 3 groups. In that case, we use ANOVA. But it's one way because it's only one factor involved. So in a situation, if let's say, in addition to that dose now, to the Viagra, we now have another factor that comes in. I say maybe we talk about white man and black man involved in the research. So in that case now, since the white and black are divided the participant into 2, while the other factor, which is the Viagra, divide the participant into 3. So when you multiply the 2, now I give you 6 groups. I'm going to have white with placebo, black with placebo, white with low dose, black with low dose, white with high dose, black with high dose. You have this 6 group. It's not because it is just 6 group, because the 6 group are defined by 2 factors. So it's 2 ways ANOVA. Of course, you can have one factor that divides them into 6. It's possible. You can decide to say, okay, even the placebo have the dose. You can say placebo, so milligram, another milligram. You can even have up to 6. If you have it like that, you have 6 groups defined by only the Viagra. It's still one-way ANOVA. But in this second scenario I just gave now, you are having the Viagra divided into 3, and you have another factor which is raised divided into 2. In that case, you are going to have 6 groups. So these 6 groups are defined by 2 factors. It's factorial ANOVA. Sometimes you can even have 3 factors involved. That would be 3-way ANOVA. 4 factors involved, 4-way. So whenever you are having 2 or more factors involved, it's called factorial design, factorial ANOVA. Now, the type of factorial design, you encounter this well, 3, independent factorial design. What we mean by independent here is that you have this example I give now, white and black and Viagra is independent because the two groups, the two factors are independent. And if you look at it, if I say a white with placebo is different from black with placebo, it's going to be different. The two of them will be different from white with low dose, and they're going to be different from black with low dose. Also different from white with high dose and black with high. So we're going to have 6 independent groups. Independent in this case means that there's no one person that belongs to any of the two groups at a time. So all those 6 groups are different people. So in that case, there are independent variables involved. That is independent factorial design. We can have repeated measure in the situation. Maybe, for example, now we can say, okay, imagine if we say, okay, the same set of people took nothing, placebo. They perform, we measure their libido. After the thing had worn away, maybe another day, they now took low dose. All of them also took low dose and went to perform. And after another time, that one has gone up, maybe another day, all of them now took high dose. In that case, if you look at the different dosage you are giving, it's not independent group. It's the same group of people. So that's what we call repeated measure. Whenever you are having the same set of people, you are taking measurement from them many times. The same set of people is repeated measure. It corresponds with pair treated. You know, when you say pair, it's only designate 2. That is 2. If you take measurement 2 times on a group of people, that's pair. And that's why we use pair treaters, because it's still 2 groups. But when you take it more than 2 times, you cannot use pair treaters unless you know to do separate pair treaters for each stage. In that case, it's a repeated measure. So now you can have miss. Can you see that the first one is independent factor? Then we repeated measure. The third one is the miss design. You can have repeated measure, independent factor. For example, now the example I gave about this, if this Viagra, maybe we gave it to the same set of people, and later we give. But this set of people, they are different, black and white. The black and white factor is independent. While giving the Viagra to the same set of people repeatedly is a repeated measure. In that case, that's a misdesign. Mixture of independent design and repeated measure design, that's all. So let's quickly, why I just want to, in this lecture, we'll look at the first one, the independent factorial design. What I just want us to realize is that the way we calculate the F statistic in one way ANOVA is a little bit, it's the same, but there's another step further. There's another step you have to take whenever it is factorial design. We have more than one factor. So it's still the same logic. You're going to separate the variance between, variance within. But that variance between, you're going to split it into the factors involved, and the interaction of those factors. So we look at it.
Yeah, good evening.
Now, in factorial ANOVA, we still find the total sum of square. Just like what I said, let me bring this annotation. You still calculate the total sum of square, which is this model. That is the model. I'm breaking into, that is the between, the total sum of square. And breaking into the sum of square model, which is between the total. You still calculate the total sum of square. You divide into sum of square between, which is the sum of square model, and sum of square residual, which is sum of square within. But however, that sum of square model, what contribute to that between? The two factors are involved. You must be able to separate the effect of the two factors, and the interaction. So three things are there. So the sum of square model, unlike one-way ANOVA, which is just one, in sum of square model, in factorial ANOVA is not just one. If it is two factors, there are three. If it is three factors, in fact, there are about six, because you talk about individual effect and their interaction. So now, the simplest form of factorial ANOVA independent ANOVA is when you have two factors. In these two factors now, you have to break the sum of square within into the effect of the first factor, which I say sum of square A. The effect of the second factor, which is the sum of square B, and the interaction effect of the two factors. I think maybe you'll be able to conceptualize it better if you see the diagram. Look at it. This first one is S total sum of square. The total sum of square, of course, is made up of two. The sum of square model, which is between, and sum of square residual, which is within. The green is the between. The purple is the within. Now, what we're now saying is that in factorial ANOVA, this sum of square between, which is the model, is divided into the component. It's divided into the factors, those factors involved. You know, if it is one-way ANOVA, it will be one, because it's only one factor involved. It will just be one. So you just calculate your head. You calculate the variance the between over within, and just rest your case. But in this case now, the sum of square between, which is the model, is made up of contributions from different factors and their interaction. The simplest form now, which is two factors, is given here, A and B, factor A and B. You will see the sum of square between will be divided into sum of square explained by variance variable A, the first variable. Then the second will be sum of square variance explained by variable B. Then the third one will be interaction of the two. Interaction of the variable A and B. An example is given here for us to be able to understand. This example, if you conceptualize, you just look at the way it is calculated. I think we'll be able to conceptualize the way it works. In a situation where somebody was trying to study how people choose mates in the party, that is, how a man chooses a lady or how a lady chooses a man, a man, whichever way, can be man or woman, how they choose mates. Now, I want to see, people like to choose people that are very attractive, like choosing people that are very attractive. Now, they want to look at the effect of alcohol on these people, on the how somebody is able to choose somebody that's attractive. Maybe the effect of alcohol can dampen that person's sense of judgment. In that situation, alcohol was given to some people who were not given alcohol. They didn't take alcohol. The second group took 2 pints. The third group took 4 pints. So you have three groups of people defined by the alcohol given. No alcohol, 2 pints, 3 pints, and 4 pints. Now there's another factor. That is one factor, the alcohol. There's another, because it's for example of factorial ANOVA. There's another factor, which is sex. We also want to see between male and female. So you have these two factors, the alcohol and the sex.
Like from this plate to this.
Now, so with that now, you're going to have 6 groups. Okay, you're going to see the 6 groups without wasting time. What happened now is that some people now, through the picture of the mate, each of them choose to see how attractive, they now give a score of between 1 and 100. How I scale of 1 to 100 to see how attractive the people they choose. Now, what I just want you to know here is that there are 6 groups now. These 6 groups are defined by the 2 factors. One of the factors is the alcohol taken. Either the person take alcohol, which is 1, which is known, or when he did not take alcohol, rather, which is known, or 2 pints, or 3 pints, or 4 pints, rather. So then either the person is male or female. So when you look at it now, 2 factors times 3, and 1 factor has 2 variables, 2 values, and the other factor has 3 values. So 2 times 3, making 6. So these are the 6 group, the score of the 6 group. Male, female that took none, male that took none, female that took 2 pints, female that took 2 pints, female that took 4 pints, male that took 4 pints. Now, for you to actually know the effect, it's initially sad. So let me just, if you have been following the example we gave on the one-way ANOVA, you will notice the way we calculate. This one just a way of simplifying it. Know that because there are 3 levels of variances. Whenever you are trying to look at difference between groups, there are 3 levels of variances you are looking at. Let me just repeat it. The first one is the total variance. Total variance means even though they are grouped like this, in this case now there are 6 groups. Each of the group is, if you look at it, is 8, 8, 8. 8 times 6 will give you 48. That is 8 female that didn't take any alcohol, 8 male that didn't take any alcohol, 8 female that took 2 pints, 8 male that took 2 pints, 8 female that took 4 pints, 8 male that took 4 pints. So you're having 6. Each of them they are 8, 8, 8. 8 times 6 is 48. So the total variance is if you add all the 48 together and calculate the mean and calculate the variance from the mean. You know, you can the way you calculate the variance is very simple. I keep on repeating it. When you have calculated the mean, how do you calculate the variance? Look at the example here. You just remove the mean from each value, that's deviation from the mean. You square it, that's square deviation from the mean. You add it together, that is sum of square. Now divide by the degree of freedom, which is the variance. The degree of freedom here means the sample size, the total minus 1. So for the total, if you have to look at total variance now among them, is 48. If you add all the 48 score together and divide by 48, it gives you the mean. And I think on the slide, the grand mean is there. Look at it. Because each of the group also has its own mean. And you see, each of the mean and the variances for each group, and we have the grand mean, which is the mean for all of them. If from the grand mean, you calculate the total variance. So if you now remove the mean from each value, or the 48 value, and now square it, that's what the first 2 columns. You know, the first column is subject, just the 1 to 48. The group they belong to, you know, there are 6 group. The first 8 group 1, second 8 group 2, 3, 4, 5, 6, like that. And you know what each group means. The first group is female that didn't take anything. The second group is the male that didn't take anything. Then the third group is female that took 2 pints. The fourth group is the male that took 2 pints. The fifth group is the female that took 4 pints. The sixth is the male that took 4 pints. If you remove the mean, the grand mean, the mean of everything from each of the value, you get this and now square it and divide. You calculate. This is total. This is sum of square. Total sum of square. No, you have not even calculated the variance now. Just for you to square the deviation and summing. That is sum of square. The total sum of square is 8,966.6672. That is the total. That one will give you the picture of the total variation. Now, for you to now know what is the sum of square between the model. The model now how you do it, because you are looking at the difference between the two groups. And the model, look at it, is the second group of this thing after group X and this first two, the middle two, X bar minus S double bar and S bar minus S double bar square. So what you do here is to remove the mean of each group. You know, each group has its own mean. You see, each group has its own mean, and there's this total mean. So what the sum of square, how to get the sum of square model or between, is for you to remove the mean of each group. You know, remove the grand mean from the mean of each group. How you know that one self is, if you look at it, for each of the group, the mean is the same for all the 8 group, all the 8 participants in the group. You can see now, when you remove it, give you a constant value. Can you see? For the first 6, for the second 6, third 6, fourth 6, fifth 6, eighth 6. Can you see? When you remove the mean, the total mean, grand mean from the mean of that class, give you this value. When you square it, when you sum it together, that will be sum of square for the between, which is the model, which is 5,479.1672. Remember that the total variance, the total sum of square is 8,966. But the model between is 5,000. You know, the model and the between and the within will be equal to the total. You know that. So to calculate the within, between, or within rather, all you need to do now is to remove the mean for each group from the value in each group. So what we do is for the first 6 now, to remove the mean of the first class from each value. For the second 6, to remove the mean of their own class from each value. For the third one, you do it so and so up to everything. When you square it and sum it, it gives you the sum of square within, which is 3,487. So if you add 3,487.5 to 5,479.1672, it will give you the total sum of square, which is 8,966.6672. Now, if it were to be one-way ANOVA now, all you need to do, just for you to calculate the sum of square, the variance, just divide the sum of square by the degree of freedom, the sum of square between and within by their degree of freedom, and now put the mean. You know, when you divide, you have gotten the variance rather. So dividing the variance between over within, that will be your F. But because there are 2 factors, you have to now go. You have just calculated the sum of square total and within that. But you need to split that sum of square between into its component. You know, because there are 2 factors, there will be one that is accounted for by factor A, there will be one that will be accounted for by factor B, and there will be one accounted by both of them, which is the interaction. So that, because there are 2 factors now, the sum of square between is split into 3. And how do we do that? Is by, look at it. You know, there are 2 factors. The factors here are sex and the alcohol. We call it the main effect of gender and alcohol. For the gender and the alcohol, can you see the left side of the table here is for the gender. The right side is for alcohol. What do? You know, the gender, divide them into 2 groups. So you are looking at the effect of gender, irrespective. What you do is that irrespective of whether the person took alcohol or not, you just collapse them into male and female. So in that case, at 48, we have 24 male and 24 female. For the main effect of alcohol, irrespective of whether the person is a male or female, you just collapse them into no alcohol, 2 pints, 4 pints. Can you see? And you can calculate the mean for each group also. The female group, this is their mean. The male group, this is their mean. For effect of alcohol, no alcohol, this is their mean. 2 pints, this is their mean. 4 pints, this is their mean. If you now all you need to do, because what we are doing is to split the sum of square model into the component. So what do you do? So for the sex now, all you need to do is to remove the grand mean, the total mean, from the mean for each of the gender. And you see now, if you look at the first 1 to 24 now, you remove their own mean, you remove the grand mean from their own mean for the female group, and for the following 25 to 48, you remove the grand mean for the mean of the male group. When you do that, you square it. It gives you it. I need to drag this thing up so that you can see. You see, when you do that, for the gender now, it gives you this sum of square is 168.7512. For alcohol, when you do the same thing for the alcohol, you know there are 3 groups. For each of the group, you remove grand mean from it, and you do it for the 3 group and square. It gives you the sum of square is 3,332.2922. So what we are just saying, that's what I came to write here. The main effect of the gender, the sum of square we got is 168.7512. For alcohol, it's 3,332.2922. If you add the 2 together, it's not up to the sum of square within. In between, we calculated, which is 5,400 something. So the difference you are seeing is the interaction effect. So if you want to know the interaction, you know, you have known the main effect of each of them, the contribution of the sex and gender and that of alcohol. So the remaining one will be it will be the interaction. So what you have to get the interaction effect is just by removing. This is the sum of square model between we have calculated before. You remove the gender and the alcohol from it. When you remove it, it gives you 1,078.125, which is their interaction effect. So now, what it just tells you is that you already know what you have just done in that step is for you to break the sum of square between, which is the model, into the constituent factors and their interaction effect. That's what we have just done. So when you have done that now, so we now calculate, you know what you have just done for them is to calculate the sum of square. You now want to know the variance. The sum of square divided by degree of freedom is the variance. So the variance for the first factor, which is sex, factor A, which is gender, is the sum of square over the degree of freedom. Degree of freedom is the entity minus 1. How many groups you have for this gender? 2, male and female. So the degree of freedom will be 2 minus 1. That is why it is 1. You now calculate the variance for sex. Then the variance for that's for gender. The variance for alcohol. So when you bring the main effect of alcohol, the sum of square for alcohol, divided by the degree of freedom. There are 3 groups of the alcohol. No, none, then 2 pound and 4 pound. So 3 minus 1, which is 2. That's why the degree of freedom is 2. When you divide it, it gives you 1,666. That's the variance. Then the interaction effect, the variance for the interaction effect is for you to bring the sum of square interaction over the degree of freedom. What is the degree of freedom? You know, the interaction, the alcohol group is 3 groups. The degree of freedom is 3 minus 1, which is 2. The gender is 2 groups. The degree of freedom is 2 minus 1, which is 1. 1 times 2, 2. That is why for their interaction, the degree of freedom is 2. No, if you cross tabulate it, it becomes row total row minus 1 times column minus 1. So we have 3 groups of the alcohol, which is 3 minus 1, which is 2. Then we have 2 groups for the gender, 2 minus 1, which is 1. 1 times 2 gives you 2. So the degree of freedom for interaction effect is 2. When you divide the sum of square, it gives you this. So of course, if you remember, we have the first calculation we did was to separate the sum of square within from between. So the within is still there, the one we have calculated, which is 3,487, when divided by the degree of freedom, which is 42. Why is it 42? Because there are 2 ways you can approach it, even 3 ways. You know, each group, there are 6 groups. Each of the group, I've said there are 8. The degree of freedom for them would be 8 minus 1, which is 7. 7 times 6, 42. That's what we are doing. Or you can say that all of them 48 divided minus 8 in 6, because there are 6 groups. 6 groups, so it gives you 42. Or you can go and add all the degree of freedom of the okay, that is one is for the total. So that is the 2 ways of approaching it. 2 ways of approaching the degree of freedom for within. So the total sum of square over 42, which is the degree of freedom, it gives you 83.036. So the F ratio now will be, you now calculate for the main effect of gender, the main effect of alcohol, and their interaction. That's what we do. Just put their variance you have just calculated over the variance within. When you do it, it gives you 2.2011. So you see, by the time if you look at it now, the smallest one is the set. When you run it, if you go and look at the table now, if you go and look at F distribution table with the corresponding degree of freedom, you will notice that number 1 is not significant, 2.032. It will be lower than the critical value. But all these 2, for the main effect of alcohol and the interaction of alcohol and gender, they are very significant. So if you, this is the step to run it. I want to run it in SPSS, and the result is here. You see there, where I just want to take you to, so that it doesn't confuse you, is where the main effect and the interaction effect, you can see as a result. Look at it. Look at this table, second table here. You will see the first one is combined. As if there is no, as if it's one way ANOVA, that is a combined. When you look at the effect of the gender, can you see? If you remember, this is the, if you can look at the sum of square we calculated for it, and the variance mean square, and the F, can you see? It's the same. And the p-value is 0.161. You know, I said before, because the F we calculated there, so it's 2.032. It's not significant. When you look at alcohol, look at the sum of total sum of square, look at the degree of freedom was 2, and mean square, that's the variance, and look at the F, 20.065. It's significant. The p-value is less than 0.01. The same thing with the gender. Can you see gender times alcohol? That is their interaction. Look at their square, means sum of square, the degree of freedom, and the mean square, which is the variance. Then look at the F, which we calculated before. This is the value, and it's significant. So that's it. Can you see? When you do it now, it will be able to give you the effect in Factorial ANOVA. It will give you effect of each factor and the interaction. I think we'll stop here. There's any, though this one also you do contrast or post up also. But I want to stop here for question. I want to stop here for question. I don't know if I'm sure you have question.
Thank you very much.
Nobody. Yes.
Question, yes.
Well done.
Okay.
Question.
No
Hello?
question. Yeah.
No, there are questions.
Okay.
Yes.
The first question, 2 questions really I want to ask.
Okay.
The first question is with respect to the interpretation of the result.
Okay.
Some argue that when the interaction effect is significant, then that's the bus stop. You don't need to go any further. It means you are not going to make reference to the main effect of the other 2.
No, I don't think, no, it's not like that. If you look at it, why do you need to separate them? Because they are different. The main effect of each of them and the interaction effect, they are different. So from the result we are seeing now, you can see on its own, the gender does not have effect. But combined with the alcohol, it has effect. That is, and if you look at the alcohol has effect. So because alcohol has effect, if you still bring in gender, It's still, the effect of alcohol is still there. That's what he's saying. But on its own, gender does not have effect. So it doesn't stop. In fact, you can still go on. If you look at it, I didn't just in this one, I don't want to talk because sometimes when you have to get it bit by bit. The contrast also, post-op also, you do contrast. So because there's effect, we know that there's no effect with gender now, but there's effect with alcohol, there's effect with interaction. Are we together? And you can actually even demonstrate, okay, I didn't show that one in the graph. You can show the way it is in the graph. Sometimes you need the graph to interpret, to understand the effect of the two, the interaction effect. Let me just go back there so that look at the graph, look at the interaction, the graph. Look at the graph. Look at the first one. This first one now is looking at the main effect of alcohol. Can you see? It is clear that the first one, no alcohol, and 2 pints, there's no difference, there's no much difference. But the one that differ, that the effect is more when you take, the person take 4 pints. No, the attractiveness, the judgment is impaired with 4 pints. So it is 4 pints that actually, if you are to ask now, where does the difference lie? The difference between no and 4 pints and between 2 pints and 4 pints. You can see, even before you go and do post-hoc or whatever contract, you can see that this is where the effect will lie. Because there's no difference between no pint and 2 pints. But the 4 pints is the one that's significantly different from the other two. And if you look at the main effect of gender, the second graph here, you see, this. Look at it. You see, there's the attraction, the attractiveness, the judgment is lower with male than female. But there's not much difference. That's why you can see there's no difference statistically between male and female when you look at the gender effect. But these two graphs down, one is bar chart, one is line graph, they are looking at the interaction effect of the two. You can see, if you compare now, no alcohol, you can still see that the red is female. You can see the under no alcohol, the female score lower than male. Then under alcohol consumed 2 pints, the female still score lower. But when they now consume 4 pints, the female score higher. That shows that the choosing mate, the score is higher with female when they are taking much alcohol. So that shows that the alcohol affects male judgment. Naturally, if there's no alcohol, maybe just no alcohol, the male will rather want to go for fine people more than female. So it shows that the female may not go for fine men or fine people, just like the way men go for fine people. But when it comes to when they take 4 pints, they are drunk. So the judgment of the male is grossly impaired. That's what it shows. So you can see in the interaction, when you look at the interaction graph, you'll be able to, it's the same thing, the line graph is the same thing showing. I think this bar chart is clear. It's easier to interpret. I don't know if there's any other question.
Yeah, just the final one.
Okay. Go on, sir.
Yeah, this interaction effect, can it also be looked at as a moderator effect or mediator effect?
I don't know what you mean by moderator or mediator.
Yes, I was even about to ask the same thing. That would you say that gender on its own is not significant, but when it is now interacting with alcohol, that is now when it becomes significant. So I think what he's trying to ask is that will you call it a confounding effect, or will you call it a
okay.
Fire? But okay, so maybe we can explain. I have another question, but
okay.
Shall I say the second question?
Okay, you can say, if you look at it from what we have just said now, It's not confounding because when you say something is confounding, like for example, if you look at it, if let's say we run in the gender, it was significant, and when we now merge it with this thing, the aqua is no more significant. I mean, that's okay. Aqua is confounding for the gender, but the gender on its own, you can see it's not a factor. But you can say that whenever they interact, yes, when they interact now, you can now see that somehow, you can see the effect of gender on the alcohol itself, because without the alcohol, without the gender, you can see how the relationship between the score and the amount of alcohol taken. But when you look at it, when you now bring in gender, you see how it is more like interaction. So you cannot actually say that one confound for the other. It's more like interaction. Go on. Ask your question.
Thank you, sir. Thank you, sir. Please, sir, I'm sorry to take you back. I'm just trying to, that 42 you mentioned.
What?
I don't know why it keeps eluding me. That's degree of freedom for 42. Can we go back to that table?
Okay.
That table.
Very...
In fact, I want to see that. In fact, I think the first thing I want to see is, that's division. There was this flow chart you had where you showed where you split when you were talking about, okay, how the between is split into 3 for the factorial.
This one? Is it this one?
No, still back. No, I will come to this one. Back. I just want to.
This one?
Still back. No, not this one, sir. That's your normal flow chart. I want to see that one first. The one that you had at the beginning.
This one?
Because I didn't see it very well.
This one?
Okay, yes, I understand this one now. So so you can now go forward. So the 2 questions I had was how you calculated that you're between, and then that 42 degree of freedom. It keeps eluding, like I don't know why it keeps slipping through my fingers. How you got that 42?
Okay, let's solve how we got the 42 from it. We can get it from this table. If you look at it, there are 6 groups. The 2 factors have divided them into 6 groups. Can you see?
Yes, sir.
You understand?
Yes.
And each of them have their own mean. So if you calculate what's the degree of freedom from each group for each group now? Because there are 8 in each group. What's the degree of freedom?
It will be 8 minus 1.
Which is 7. So when you multiply 7 times 6. 7 times 6. Because each of the group has degree of freedom 7, 7, 7, 7. In 6 places, that's why the degree of freedom for within is 42. You get it now?
Yes.
You know that if you come here, all of them, this table you see, where we calculated it, the last 2 columns is the one that look at the between within. The last 2 columns is the within.
Which is the x minus the mean? That's the mean or the grand mean.
Yes, x minus the grand mean. So x minus the grand mean, if you look at it for each of the group, you have already listed them. If you look at it, there are 48. And all the 48, they are not in one group. If you look at the group now, the first 6 is one group. There are 6 of the group. There are 6 groups. So the degree of freedom for each group is 7, 7, 7, 7, 7 in 6 places. That's why the degree for the within is 42. 7 in 3 places, in 6 places. You get it now?
Yes, sir.
Yeah, you get this one now, right?
I do, yes.
And we're talking of the between. Is it the degree of freedom between that is giving problem or what? What is the problem?
No, I wanted to see how. I think I know. I wanted to see how you calculated your between.
Between.
But what? I remember now.
Between sum of square.
Yes, for the sum of square between. But I just remembered now.
Follow. If let's say is this first one you see. If let's say is one-way ANOVA now, it's not factorial. All our judgment will be on this one alone. This I will calculate the between now because the middle one, the middle 2 column is removing, what he remove is remove the grand mean from the mean of each group.
Yes, sir.
And that one is easy to recognize because you will see that for each group, the value will be the same because the mean for each group is the same for all of them. That you examine,
Yes,
if for group 1 now, it's going to be when you remove the grand mean from the mean of the group,
yes,
it's the same value you get for the 6, for the 8 in that group. Then for the 8 in the other group is the same value. For the 8 in the, because the mean is one mean for each group. You understand? When you remove the grand mean from the mean of the group, it will give you this, that's how you code the same value for each of them, for each of the members of each group. So when you square it, that's what they give us the between, which is the model, which is total. But with this between, we want to split it into the component part for the for the factors. And that is the only one we went to. If you look at the notation, if you go to the next one we did, it's only for the gender, it's only the between we did. Grand mean minus the group mean. That's all we did for both gender and aqua. So for gender, what it just does to assume that all of them are divided into only male and female, and each male and female has their own mean. We now remove the grand mean from the mean of each group. For the gender now, 1 to 24 is for female, then 25 to 48 is for male. So remove the grand mean from the mean of each female and male. If you look at it, for the first 24 now, it's the same value you are getting. For the following 24 for the male, it's the same value you are getting. When you square it, this one is that between issue. The one contributed the main effect of the gender is what you have here. So when you now come to the alcohol, if you look at it, the alcohol divided into 3 groups. There are only 3 groups. So you're going to have 16, 16, 16, 48, irrespective of whether you are male or female. No pint, 2 pint, 4 pint. So you're going to be 48 divided into 3 with 16, 16. The first 16, the next 16, the next. So that is why when you look at each of them they will have their own mean. When you remove the grand mean from, that's why you're having the same value for the first 16, second 16, the last 16. So when you require it, it gives you this 3,332.2922. This is the main effect of the alcohol. This one is the main effect of the gender. When you now come to the now, what I was now saying that for you to be able to, this is what we got for the gender, this is for the alcohol. If you have to both of them together, it's not just up to the total you calculated before here. Total, the between you calculated before. The between is 5,479. So the contribution of this one, the extra is their interaction effect. So that is why if you want to get the interaction effect, you remove the main effect of gender and that of alcohol from the between you calculated before to get the interaction effect. So when you now want to calculate the variance for each of them now, you now calculate the main effect and the main effect of alcohol in gender, which is A, number 1, is the first one. The range of gender, you divide the sum of square for the gender divided by the degree of freedom.
Yes, sir.
There are 2 groups of the gender, male and female. So 2 minus 1, 1. Then this second one is the main effect of alcohol divided by the degree of freedom. There are 3 groups of alcohol, known 2 pint, 4 pint. So the degree of freedom is 2, 3 minus 1, 2. Then the interaction effect, the interaction effect you calculate over the degree of freedom for the interaction. The degree of freedom for the 2 multiplied. So the degree of freedom for sex is 1, for gender is 1, for alcohol is 2. 1 times 2 give you 2.
Yes, sir.
The degree of freedom for the interaction is 2. Then for you to calculate the F for each of them, you are going to divide each of them with the within. So the within, the variance within now. Now we have in the first table we have calculated, the total sum of square within 3,487. So that 3,487 divided by the degree of freedom. That's the one that is 42. That is each of the group is 7777. 7 times 6, 42. You get the variance within. So for you to calculate the F ratio for main effect of alcohol, for main effect of gender, and the interaction effect, those are the things. You divide each of their variance over the variance within. This one, if you look at all of them, it's divided by 83.0236036. Look at it. That's what we do. That's how we calculated the F for gender, F for alcohol, then F for their interaction.
Yes.
That's just a summary. Is
Thank
it difficult? It's not difficult.
It's not to. Thank you, sir.
Any other question? Any other question?
Hello, Dr. Dolapo.
Yeah, go
I'm
on,
just wondering, hello.
Yeah, go on, sir.
Sometimes when if you have an experiment where you have about 2 or more, which also includes a control group, like this one you did for us now.
Yes.
Those who had no alcohol, can they be seen as the control group for that?
Yes, actually the control, yes, is control.
Okay, so the control will also you need to also calculate all those
control. Once each of them, they are a different group. So it's not better whether it's control or it's the group. There are 3 groups.
It's the group that matters.
The group. So, and when you have 2 groups of alcohol, then you have 3 groups of alcohol, 2 groups of sex, it gives you 6 groups. Can you see now? It gives you 6 groups. If you have another factor now, it will make it more complex. If you have another factor that divides into 2 groups also, maybe we say white and black also. In that case, you are going to have 12 groups. Total. You understand now? It will be more complex. Dr. Taiwo, you want to ask a question? Dr. Taiwo?
No.
Okay. Okay. Dr. Adetuji now. So I think if there's no question, if you don't want to, you can type it. If there's no question, maybe we just end it here. And people that are coming because this weekend, let me just off the